Hi, my name is Jorge Garcia, and I am a Community Manager with Fusion 360 Electronics and Eagle. Welcome to Episode 4 of our A to Z project tutorial series. In this episode, we're going to jump headfirst into the layout. This episode will be totally focused on the 2D PCB, and by the end of it, we'll have a fully laid out PCB ready for manufacturing. So let's go ahead and get started. Now for this PCB, this is where we left off. We're going to be working with the edit and workflow, the edit and place PCB. That's the one that I'm going to continue the rest of the way. And one thing I'm going to do is I don't want the holes. I'm just going to go ahead and save the design, close the data panel. Let's go over here, the edit and place workflow PCB. Go to the enclosure. Let's go ahead and do an edit and place. Okay, I'm going to use the same context, now making a new one. Okay, and I'm going to go right click, edit board. And for the profile, I just want to include these, that way they're closed. It's just a solid board. Say OK. All right, finish the edit in place. Okay, I'm going to go ahead and save. I'm going to say I remove the holes. So I have more real estate to work with. And the finished board, it'll be mounted through the potentiometer, so it really doesn't need any holes on the PCB itself. Now we go to our PCB. We see that it needs to be updated. We select it. You want to discard? Yeah, I do. Okay, it updates. Good. Now we push to the 2D PCB, and then from here we push back. Okay, so this is just a really brief recap of what we did in the previous episode using edit in place. So at this point, I'm going to go ahead and save the design because from here on out, we're going to be focused on the 2D PCB. I'm going to hit save, and I'm going to call it ready to start the layout. Say OK. Perfect. Now let's go to the 2D PCB. We can see this is the area we have to work with. And the first thing we want to think about is, are there any components whose position is kind of already dictated for us? Okay. Now this is a board that's intended to be interacted with, obviously with 5 knobs. So ideally, we would want to locate these knobs in such a way that they're easy to work with and that their position can be in a very natural and aligned way. So what I mean is, having them in a row, being able to arrange them in a logical fashion. Because if we start doing the circuit layout, and not take this into account, what may end up happening is that we end up with like a potentiometer up here, and then another one over here, and things like that. So because I know the potentiometers are a human interface issue, what we want to do is go ahead and put these down first. Okay? And what can sometimes inform that is we want to organize them in a way that may be natural. So I'm going to go over here, look at the schematic. We have this input potentiometer. Then we have these, which are kind of like gain and adjustment potentiometers. This is volume, and this is EQ. So what I'm going to do is we're going to go ahead and put RP1 first. Then we'll put in RP2, RP3. Because those deal with gain and altering that. Then we'll put RP4 and 5 again. Actually, I'm going to put volume first, RP4. Let's go ahead and do this. So volume is going to be up here in the top left corner, kind of around this area. Okay, so that's volume. Next, I'm going to put the 2 gain adjustments, right? Because we have this RP2 and this RP3, and they affect gain kind of in different ways. So maybe on the PCB, I'll highlight that. We're going to put RP2 and RP3 next. I'm going to take this over here. I'm real close. more or less here. I'm gonna arrange this. I'm gonna try to put them in a line, kind of as best as I can. Okay, and then RP1, which is the input. We can put this one like maybe right here. And then RP5, which is the tone, would be right here. Okay. That's just a rough idea. We can align them a little later, but we know their positions are going to be pretty much fixed, and we want to keep them related to each other. I'm going to move them up as much as I can. I'll put that right there. And we'll take these, we'll move them up as well. Okay, and this will look nice. Maybe I'll leave a little space, and what I can do is I can take this LED and put it in the middle, put it between them. You can use the Alt key. When you're doing a layout, you can use the Alt key, and that'll give you a finer grid. Okay, so you see I'm moving. If I let go of Alt, and it's a coarser one. Okay, so this is just a preliminary kind of move. Have everything kind of in the same area. Now, right now, I'm not too concerned with the fact that the text is being overlapped. That's fine. I can always move it around later and get things sorted out better. So right now, I'm looking for aesthetics on the finished PCB, because when I put this in the enclosure, I want this to be comfortable to use. So, you know, no pots all over the place. So that's fine. Okay, next thing. Any terminals that need to be in a certain place. So this is our power terminal. And I expect to kind of have the power connector near the edge of the board. Near one of the edges at least. So maybe the top one, maybe a side one. Let's see over here if this is going to be okay. Now, if we get too close, what you're going to see is it's not going to let you get any closer, because it's going to keep respecting the design rules. Now, the default design rules are extremely conservative, and this is to make sure the board is always manufacturable. Okay, for now, I'm happy with that. I can always change it later. It's just kind of a roughing in where everything is. And I know this is definitely going to be near this edge of the board for sure. Now, if we go back to design over here, now you'll notice that it'd be really nice if all of these are kind of aligned vertically. So what I can do is I can select this component, I can select this one, I can select this one, and I can select this one. And I want these to be aligned vertically. Well, we have the align command for this. Okay, and we can choose the type of alignment we want to have. See? So bottom edges vertically. Let's pick vertically. And I picked the wrong one. So if you pick the wrong one, that sometimes happens. Control Z. You can just Control Z, do this again, and we can pick align horizontally, which is what I think we want to do. Align to grid right here, this one. Align centers horizontal. There we go. That's what I want to do. So sometimes that happens. It's okay. I click OK, and you'll see now there's a straight line that goes between these. And maybe even move this one over a little bit. There we go. So right now this is looking pretty good. I feel pretty good with how these main components are aligned. Now this diode, it isn't very critical where it is. I'm going to try to put it maybe over here. If it's up here, because it's going to be near. It's part of the power circuit, so it makes sense to have it close to it. But I could locate it anywhere else. So I'm going to just kind of put it right here for now. I think that'll be just fine. Okay. Now, you notice we have the rest of these components. Where could we place them? Well, we have a lot of options where we could place them. I could decide to put everything at surface mount on the bottom of the board. That's not a bad idea. I could put the transistors on the top of the board, since everything through Hall I can have them all mounted the same way. That'll make soldering easier. You know, I could choose to maybe solder everything as through hole first. Actually, no, we would solder everything that's surface mount first. And then because everything that's through hole is on one side, it's going to make it easier, the soldering process. So you can sometimes divide things up that way. If your circuit had very specific requirements, if it was processing, you know, high power signals, it was RF, it was things of that nature, very sensitive, maybe like low level analog signals, then you would have additional constraints involved. But because this is a simple circuit, it is pretty robust. It's not dealing with any high frequencies. This is strictly audio range, and we have a lot more flexibility with the routing. So what I'm going to do is I am going to put the transistors on the top of the board. I'm going to put them kind of in a general area, put them together. And then I'm going to take all the surface mount components, put them on the bottom of the board. That's how we're going to kind of approach this. You'll probably see that I'm going to speed up this part of the video because I'll be arranging and routing things for a while. If I see anything that's worth noting, then at that point the video will stop and I'll talk about it, and then the video will continue speeding up. But the process is going to be pretty much the same. So I'm going to go ahead and move these. I'm just left clicking and dragging. Now notice right here how I kind of selected the air wire. And if you find that to be cumbersome, over here in the selection filter, you can uncheck air wire. And that way air wires are selected from, are excluded from selection. So I can just click, left click and drag, and it'll grab the component because now the air wire is not being considered for selection. One thing I want to mention while we're here is you'll notice that anything you do on the 2D PCB is going to tell you 2D and 3D PCB are out of sync. And that's true because the 3D PCB is showing, you know, everything off in space over here. Whereas the 2D PCB, I've already started to kind of locate things. So what we can do is I can push along the way and just kind of get an idea of how things are looking. And you can see this is starting to look pretty good, pretty favorable already. Okay, and the fact that I have a library that has all the models already in it makes things easier. So let's go back to the 2D PCB and we'll continue just making changes. So that's going to pop up again as soon as I move this transistor. You'll see it pops up again. You can choose to ignore it, and that's what I'm going to do. So you're going to see it for quite a while here in the video, but that's okay. Now, I'm not too concerned right now about the text overlapping because I'm going to fix that later. One thing that's going to guide layout or can help guide layout is if you look over here on the schematic, remember how we broke it into sections? That can kind of guide how the layout should be. So we already know we have this power section over here. So what I can do is I can select these components and I can use a special ULP to select the components on the board side. So let's go ahead and do that. So I'm going to go ahead and select these components. I'm going to go to Automate, select ULP, and we have select schematic group to board group. Say OK. We can see that it ran. We have this component selected and we have this capacitor. So we already know this capacitor can be close to these components over here. Let's go ahead and figure out what's the best place to put it. Let's go ahead and grab it. Now, if you want to move a component from the top to the bottom, while you're dragging it, if you click your scroll wheel, remember how I said 3-button mouse is your friend here, you'll see it'll turn blue. And that means that it is now on the bottom of the PCB. Let's see where I can put this, that it won't get in the way. You don't want it to be too close to any pads because those will be difficult to solder to. You don't want to have it anywhere where it may not be favorable. So what I'm going to do is I'm going to put it here for now. This is a fine place to put it. I'm going to put it for now here. Later on, I can make adjustments. All right, we're going to go back over here to the schematic. Let's go ahead and put these components together. Again, we've selected the group. We made the selection. Click the UOP. I can again run it. Remember, select schematic group to board group is your friend. We'll see now that it's highlighted. I can go down over here. Now again, if I click the wheel, put it on the bottom, I can pick a little spot to have it. Let's say for now here is okay. And again, I'm not too worried about the text for now. Kind of arranging things roughly. Now, here at this point, I've come into a situation where it may be more sensible to switch the locations of these two pots. And here's the reason why. Right now, I have this capacitor here taking up a lot of space right here. The transistors are here as well. So if I put this knob on this side, I take this capacitor with me, and now I have room to bring in this capacitor. Alternatively, another option is to move the transistors over here, because all of this circuitry is associated with the transistors. So I have that option as well. So either one is an option, and what I may do is I may choose to just move these transistors over here and then bring in this component over here. So let's try that first. Sometimes layout is an iterative process, and right now it's just to get a basic layout down. There'll be a lot more fine-tuning later. I'm going to put you here. Now, one thing you'll notice right here is it's an error. You're getting this error message here. And that's letting you know it's too close. You have a violation. So we move it away. We can put it right here. Now, one thing I want to highlight is notice this mode right here. Now, these are the ignore, push, and walk around violators options. Now, these options are applicable to the layout editor as a total environment. So you notice when routing, if I have push set, then the traces can push around and make room for themselves. If I have walk around, they won't move anything, but they'll treat it as a wall and they'll try to hug that wall. If you set it to ignore, then everything is fair game. You can violate things, you can violate different parameters, you can make things that would break the rules. So ignore violators is something you will use very sparingly, if ever. Most of the time you'll be in push and walk around. So I'm going to put it in push. And you notice if I do that, it won't be allowed to get any closer to the edge. I'll put it there. Okay, and right now, we've at least verified that we have enough room for everything, which is a good sign. We have enough room for everything. I'm going to go ahead and maybe tighten this up a little bit, bring this one down. And we actually have more than enough room. So now what I'm going to do is I'm going to take, again, go back to the schematic, and I'm going to take each section individually, and I'm going to try to tighten it up as much as possible. So I'm going to have the different capacitors together, things like that. Just have everything as tight as possible. So I know my tone control is this one right here. And it involves these components and this potentiometer. What I'm going to do is I'm going to grab these, and what I can do is I can make sure it's just the bottom items. So let's actually take these one at a time. I'm going to put them right here. And this is a part of the design process where having it printed out can be helpful. That way you don't have to jump back and forth between the schematic and the layout. It makes it very easy to see what's supposed to be close to each other. So let's go ahead and continue the layout process from here. What I'm going to do is let's go ahead and print. So to print, you go to Document, click here on the printer. At this dialog, you want to resize it. Make sure you have your printer selected. I want it to be a scale of 1. It fits now. I don't want it mirrored, so make sure you have that option unchecked. And if you want to do it, just black and white, if you want to make all the different print options are here. So I'm happy with this. I'm going to go ahead and print it. And this is something I recommend you do as well. Now, once you have the schematic printed out, you won't have to refer to the schematic file anymore because you have it in paper and you can see what goes together. For a simple design like this, it's really helpful. For something more complicated, maybe the schematics are really big, it may be harder, but I still like, maybe I'm just old-fashioned that way, but I like having the printed schematic next to me and referring to it. Now, you'll notice that there's a lot of air wires here, lots of connections that need to be made. But one thing that I always recommend, unless you have a really good reason to not do it, is to put in a copper pour, a copper plane. Copper planes have a lot of benefits. They avoid warpage in the PCB because you have an even distribution of copper all over it. They provide shielding against noise. They give you a solid ground. They improve your signal integrity. Basically, unless you have a really good reason to do it, something like maybe an RF application where you have an antenna and you don't want to have the ground plane beneath it, unless you have a really good reason, always make a ground plane. And that's really easy to do in Fusion Electronics. If you actually click on the contour and you right click, you'll see this option convert to Polygon. What we want to do is we want to select copy. I'm going to select copy. Now I'm going to put a ground plane on the top. Now I'm going to explain why in a second. Okay, and you see now we have the plane. Now the command is still active, so you want to go ahead and hit escape. Make sure you don't run it again. Now let's go ahead. If you zoom in, you're going to see you have the dots, which are the polygon outline. If I left click, you'll see the cursor changes to point in the four corner directions. This is just letting you know that Fusion Electronics is not sure which object you want to select. When you see this, you can right click to cycle through nearby items. Once you land on the item you do want to adjust, you left click. Okay. Now this over here is the inspector. The inspector shows you the properties of a single object or of a collection of objects if you have them, if you've made a selection. What we're going to do here is I want to make sure to name it ground. Okay, I want all of my ground connections to be made here. So I'm going to type in ground, hit enter. It's going to say, do I want to connect it? We're going to say yes. Now if we zoom out, you're going to see that anywhere there's supposed to be a ground, we have this type of connection. Now this is called a thermal connection. Now you may wonder why is this here? Well, if you think about it, copper isn't just a really good conductor of electricity, it's also a really good conductor of heat. So if you just have a solid copper plane, when you try to solder to these pads, that copper is going to wick away the heat, and it makes it harder to make a reliable solder joint. So by just having these thin connections to the pads, what you end up having is you end up increasing the thermal impedance, so heat can build up because you don't just have a solid plane of copper, you have these thinner pieces of copper that are conducting the heat away, and that leads to more reliable connections. So the nice thing about this is that everywhere that you're supposed to have a ground connection, you'll notice that it's already made. So it eats up some of these air wires. Now what you will notice is I put the ground plane on the top. So anything on the bottom that connects to ground can't connect to it right now. But we can go ahead and fix that. So I'm going to turn off the polygon just to make it easy to see. And what I'm going to do is we're going to use the fan out command. So you see over here we have fan out. We can go ahead and pick fan out. You're going to notice that you can do fan out signal, fan out pad, etc. You can select the style for it, violations, etc. So I'm going to leave it with the 6 mil trace width. This is actually fine because we haven't done any traces yet. But actually, before I do that, let's go into DRC and adjust some rules. Now, one thing that's really cool is if you notice when the polygon isn't filled, it shows you where it filled to and where it connected. So you still have an idea of what the polygon is reaching, even though you don't have all the visual noise of having it completely filled and covering up pads. So this is a good time. Let's go into the DRC and let's just set up some minimum widths and things like that. So let's go into rules DRC. Now the DRC is a very, very important aspect of electronics design. Basically here you define your manufacturing tolerances to make sure that your board can actually be built. So what you want to do before you get too deep into the layout is make sure you set up your layers, your clearances, so that they match whatever your board manufacturer can do. Once you've done that, you'll know that any errors that the DRC pops up are legitimate errors that your manufacturer would report to you and say, hey, I can't build this board because it doesn't meet my tolerances. So let's go into the layers tab. And we have a simple 2-layer board. And that's what this is going to be. For your first project, let's stick with simple 2-layer board. Default clearances is 6 mils for everything. So the separation between any object is a minimum of 6 mils. Now, keep note that I'm going to be using the word minimum a lot through this. When you're dealing with DRC, when you're dealing with net classes, which we may not use in this board, you're always talking about minimums. So it's always okay to have more room, but at a minimum, we need this amount of space between copper features. And generally, you'll set all of these the same. Distance, this is the separation between the edge of the board or any type of cutout feature and the polygon itself. 40 mils is really conservative. Most board houses have no problem doing half. So what you're going to notice is if I make this slower, I'm going to make it 20. And I press apply. You'll see that the polygon outline went away because now the polygon, when it recalculates, is going to get closer. So if you make any changes, that leftover outline, so if you move a component, anything, that outline goes away, letting you know that the polygon needs to be recalculated. Sizes, I want minimum width of 6 is fine. Any board house can do it. But generally, I like to go with as thick a width as I can that the design will support. That way, you have better current carrying capacity. You have more robust connections just because by virtue of the fact that they're thicker. So for something like this, I have the room. I'm going to go with 10 mils. Annular ring settings are a deep subject. Generally, I'm going to recommend leave these as they are by default unless your layout starts to get very tight. If it does start to get very tight, then you'll want to look into what your board house can support as the annular ring. Basically, annular rings, if you look at all these vias, you'll notice that they have a green circle. All these pads, they have a green circle around them. That's the annular ring. That's a thickness of copper around the pad that you can solder to. Now, you need to have a certain amount of ring for 2 reasons. Number 1, you want to be able to solder reliably. And number 2 is board houses, when they drill a hole, if we look here in Fusion Electronics, all the holes are perfectly centered. But in reality, when a manufacturer starts to drill the holes, that has a tolerance. They can miss by a certain amount. And depending on that tolerance, that's going to dictate how thick this ring needs to be. Because you always need to guarantee that the hole is within the boundary of the annular ring. If it's not, if it goes past it, the via will break and you won't be able to, that part of the circuit board will fail. These are good conservative values. Again, unless you run into a part that has really thin annular rings, you won't have to touch them. Shapes allows you to basically do shapes that are different than what's in the library. Generally recommend leaving this alone. Supply tab, also not something you're going to have to deal with, but it basically controls how much separation there is in the thermal, how much the minimum separation needs to be in the thermal. Mask, this one can be often adjusted. Basically, it's how much extra opening you have around the copper elements in your design. So in order to be solderable, you need to make sure the annular ring or the pad is fully exposed. So to, again, talking about tolerances, normally board houses will ask you to give me an extra 2 mils around each pad or an extra 4 or whatever, an extra opening just to make sure that that copper is guaranteed to be exposed. 4 mils is a good conservative amount. Many board houses can do 3 or 2, no problem. And the miscellaneous tab, you don't have to worry about adjusting. We won't be doing differential pairs or anything like that here. So I changed the distance and I changed my minimum width. So I'm going to say apply, and say cancel. And now if we go back to design and we fill in the polygon, just to show it, you'll see that it gets closer to the edge than it was before. And if you saw earlier, this only had 3 connections. Now it can have the 4 because the polygon can get closer. So now let's go ahead and go to the fan out command so we can make those connections that we want to make. So I'm going to, again, unfill the poly, hide all the polygon 4 fills. And now we're going to use the fan out command to make these quick connections to the ground plane. These short connections that'll basically drop a via to connect to the ground plane. So again, let me see here. Yeah, this is component, this is signal. This is a style. If we had like, ICs here, then sometimes you need to alternate so that everything can fan out. Trace width, I'm going to have these be 10. And we're going to use a normal via. So what I'm going to do is I'm going to click on the ground net. Now in order to be able to click it, I need air wires to be selectable. I'll go ahead and click here. You're going to see very quickly all of the ground nets will drop these vias. So we zoom out, anything that connects to ground will get these little vias. And that guarantees a nice solid connection to the polygon. So this is good signal integrity. It'll improve noise because you have a quick connection to the ground. They all have similar impedance to ground. Lots of good things happening here. So at this point, I'm going to go ahead and just start arranging and routing things. And you may notice me moving things around. If anything is noteworthy, I'll stop the fast forward and talk about it. I'm going to go ahead and start routing. Now, I'm going to be routing on the bottom because I'm down doing the SMDs. Notice it took the trace width, what the bends are. I have that push violators on. And notice what's going to happen. It's going to, you see how it tries to push and make sure it doesn't get too close. I'm going to have these on 45s. Now you'll see I've made this little cluster over here. And things are starting to get dense. Now, one thing that's very common is you don't show the values of the components on the PCB just to save space. So I'm going to go ahead and click on my layers tab over here. And I'm going to turn off T values and B values. That way we don't have to worry about seeing them. So at this point, I've arranged this a little bit here. I'm going to go ahead and route it, and then we'll go from there. One thing I want to highlight here is if you notice, you have a segment that's like filled differently. Probably in your case, it'll be clear. And then as you left click, it becomes solid. So the part that's differently filled, like I said, will probably be empty in your case. That's the part that hasn't been set in stone. Whatever's in solid color is already kind of a fixed segment. So notice I can keep going. You can hit backspace to undo, and you can undo all the way back to the beginning. Here we're going to see the push feature start to come into play and see how it's pushing away. Again, we can use Alt if we don't want it to have to push too much. And another nice thing you can do here is you can just reroute a segment, and whenever it meets up again, you'll see it gets rid of the extra segment. So that can be very helpful also for reworking parts of the circuit. Okay. I'm going to use the move command just to kind of bring this down so it's not so extreme. You can use Alt. And you'll see it preserves the angles, makes it real easy. There we are. Excellent. So now the tone part of the circuit is done. Let's go ahead and work now on a different part. Now notice that I've made a very conscious effort to try to route everything on the bottom as much as I can. And the idea behind this is the more I have on the bottom, the less I have on the top, affecting the ground pour. I want to keep that as continuous as I can. So I want to minimize the number of segments I have on top of the board. So that's why you'll see that at certain points I'm like trying and adjusting and moving things around, trying to figure out the best way to proceed. Now, I would be remiss to not show you the some of the assisted routing tools, like the quick route tools. And these are handy for simple situations, but remember, use auto routing with care. Make sure you know when it's applicable, when it's not. In a simple design like this, I could just as easily let the whole board be auto routed, but I do want to kind of do it manually, because as I go manually, I'll be able to show you different little tips and tricks as we go. But just to show you kind of how these work, I select AirWire, and I can just click it, and it'll route it on the bottom. So for short distances, things that are close together, this is a good thing. It can save you some time. For longer distances, you're probably still better off doing a manual. Now, if you notice here, it did this little angle. That can be cleaned up using the smooth. It'll try to minimize the number of segments. See? So I cleaned it up, brought it back to normal. To how I would have routed it. So the quick route tools can save you a lot of time when it's like tedious connections, really short. You can just left click them and knock them out that way. You also have quick route tools for doing multiple air wires at a time. Guided is useful in more sophisticated circuits, and of course the auto router. But for now, I just wanted to let you know that they're there, and then you can explore them at your own leisure. I'll keep routing manually for the rest of this video. Now right here, I'm going to have to transition, and you can put a via on the end of the wire just by hitting spacebar. You're basically transitioning to another layer. If I had multiple layers, doing spacebar would keep going layer by layer. But for this, what I'm going to do is I'm going to switch to the top, and then I'm going to connect at the pad. That way I have the connection. So it'll be a short top segment. You'll see it went red. Now, whenever you can, if you go perpendicular to an existing trace, what that will do is it will avoid any coupling between them. So when traces are perpendicular, you don't have any noise coupling across them. And this is a good way to keep your design noise free. It's little things like this that add up, especially if you have a longer trace. Again, on this board, makes no difference because it's such low frequency. But it's good to be aware of. Alt, and again, the shorter the segment I can do, the better off I'll be. So at this point, all of our connections have been made except for the power rails. Now, if you remember, I did a polygon on the top to make a nice solid return path. I could make a polygon on the bottom as well. It'll take up whatever space is not used up by traces, and I can use that to connect the 9-volt power supplies. So let's try that. Again, we're going to use, let me go ahead and reset the selection filter. I'm going to make sure I'm only selecting a dimension line. And by dimension line, I mean an outline. Line. Okay, I'm going to right click over here, convert to poly, copy again, this time on the bottom. Okay, and this one, we're going to go ahead and make sure we can select polygon edge on the bottom. Escape because the command's still active. See, it was still active. Control Z on that. There we go. And we make this one plus 9V. You say yes, and there we are. Everything that should connect to that polygon is now connected. Now, I don't see any air wires left. Now you'll notice it's rendering the blue as the main layer. If I switch the active layer to top, then we can see what's on the top. And it looks, reset. Looks like something happened here. Oh no, it's there. Good. Let's make sure they all fill. There we are. Now we can see everything is fully routed. Now at this point where it looks like everything is fully routed, I would run a Drc check just to make sure we don't have any air wires. So we hit check. You'll see at the bottom here, no errors. So we are set. We don't have any design rule violations. Everything is perfectly done. So at this point, we technically have a board that can be functional and that can be manufactured because we've already compared it to our DRC. One thing I'm going to add is I'm going to add a little bit of text since I have some space over here. And I'll probably add in an Autodesk logo. So I'll go ahead and show you how to do the text. First, I'm going to unclutter all of this. I'll hide all Polygon port fills. I'm going to go to Document, use the text command. Okay, you'll see that it's here, it's active. I'll call it A to Z. If you just keep typing, it'll all be on one line. If I want to put them on two lines, then Shift and Enter. Okay, and you can use different fonts, you can do different things. Now the layer to put this on is actually T-place if I want it on the top, T-place if I want it on the bottom. If I want to change the alignment and I want them centered, center would be where it grabs onto. Bottom left is the default. So I have that. I can put any type of font that I want. Vector is usually what we use for the board, but I could use, for example, a custom font. And let's use one of the, this is one of the Autodesk ones, the artifact. Use this A to Z fuzz. I'll put it there. And you'll see the text stays and I can keep adding. If I'm happy with it, I'm done. I don't need to add any more text. I'm going to put OK. Now I can just move it around. If I wanted to edit it, I can do so here in the inspector. Now at this point, I've written some text. I want to put in an Autodesk logo over here. So what I'm going to do is I have to figure out how much space I have here that I want to use for a logo. And then I can go through the import process to add it in. Now this isn't strictly necessary for your first project. So I'm not going to show that part of it. I'm just going to, actually, let's just leave it. I'm going to leave it with just this text and we'll move on from here. So at this point, we've run DRC. Let's go ahead and push this over to our 3D PCB. That way everything is nice and up to date. And actually, before I do it, because I want the polygons to show up, I'm going to fill the polygons. Show all polygon port fills. I'm going to push to 3D. Do the full push. You'll be able to see we have our 3D PCB. Now, one thing I want to highlight here is that this is all solid geometry. This is not a picture. So if you notice, I can select the traces individually. I can, these are all actual elements. So it's selectable. If we do a thermal sim, the thermal sim will be taken into account. Everything. So this is very, very powerful. It's a lot more than just an image. And go ahead and put it in home view. We can look in the back. We can see all of our components, where they're located. Now, I'll notice that I have my reference designators kind of in bad places, so I will relocate them now. But that'll be pretty much it as far as making sure that this is ready for manufacture. So what I'm going to do is, let me go back to the board and let's clean this up. And now I'll push it. There we are. Everything is nice and readable. Excellent. we're going to leave it here for episode 4. Thank you very much for joining us in this series. In the next episode, we're going to be going through generating your manufacturing data. That way you can actually get the board produced. So thank you very much for watching. See you next time.